We are now going to look at another example of applying standardization to compute a normal probability. However, this is a very special case, and quite often one of these does occur in an exam question. So we are going to continue looking at our situation where we are looking at the average number of hours of study per week of students. Okay, so just as a reminder, we had X had a normal distribution with a mean of 22 and a variance of 6 squared, okay, namely 36. However, now I'm going to select a simple random sample of university students. So let's say I just pick a particular group of students in a certain lecture hall. So clearly my sample is going to have a sample size. Let's say my sample size is 225 students. And I want to compute the following. So my question is, what is the probability that the average number of study hours for, based on this group of students is between, let's say, 21 and 23 hours? So in symbols, how do these words translate? I want the probability of being between 21 and 23. However, notice a very important thing here. My random variable is no longer X, okay? I'm not looking at just a single student in isolation. I've now selected a random sample, in this case of 225 students, and I'm interested in the average number of study hours. So my random variable now is X bar, namely the sample mean. Okay? So I'm no longer going to work with just the X value over here. I'm instead going to be working with X bar. So I need to work out the distribution of X bar. Now, as X has this normal distribution, X bar will also have a normal distribution, and its mean will be the same as before. So in general terms, this will give me a mean of mu, but the variance of X bar is sigma squared over n. Okay, so just to emphasize, so in general terms, X would have a normal distribution with mean mu and variance sigma squared. So notice that this mu here is the same mu here, this sigma squared here is the same as this sigma squared here, but the additional thing to remember is that for X bar, the variance term is dependent on our sample size, namely n here. Now clearly you can see that we are dividing by n, so as I increase my sample size, so as n gets bigger, then the variance of X bar will become smaller. Okay, because for a given sigma squared value, if you divide by a bigger number, this will give you a smaller number. So the variance of the distribution of X bar will become smaller and smaller. Okay, I will do in a separate recording just a little more in-depth explanation of this thing called the central limit theorem, because some of you may be a little bit confused having read that in your subject guide. So look at the next recording for a quick review of that. Okay, but back to our particular problem at hand here. We have the following. Okay, so X bar has this normal distribution with mean mu, variance sigma squared upon n. So for our particular problem, let's say here, X bar will have a normal distribution with mean mu of 22 and variance sigma squared over n, which I can write as 36, which is sigma squared, divided by n, okay, so divided by 225. So just be very aware that we are now working with an average X bar rather than an individual entity X. However, once you've got to this stage, it should be fairly straightforward to proceed. We now apply our standardization not now to the X variable but to the X bar variable. So notice here that X bar does not have a standard normal distribution. Okay, it doesn't have a mean of 0, it doesn't have a unit variance. So in order to use table 4 from the new Cambridge statistical tables, I have to apply my standardization to X bar. However, one little thing to remember, which I will just explain. In my traditional standardization, Z was equal to X minus mu over sigma. Okay? But when my X becomes X bar, okay, so the variable I want to standardize is now X bar, in order to get Z, we now have X bar. Again, I subtract the mean mu, but I no longer divide by sigma, I divide by the following. I divide by sigma over root n. Now, just to introduce a bit of terminology, which we will return to later on when we look at the issues of statistical inference. Let's go back to red. This sigma here Why did we use that? Well, it's just simply the square root of this term here. Okay, so in my standardization of x bar, I still use the same sort of idea. The term down here is going to be the square root of the variance of the variable. What is the variance of x bar? Well, that is my sigma squared over n, i.e. this thing from up here. Okay, so I take the square root, so the square root of sigma squared upon n is just the same as sigma over root n. Okay, that's just some simple algebraic manipulation there. This has a particular special name, and we call this thing the standard error of x bar. That is an important term. We will come back to it in much more depth when we look at statistical inference, namely hypothesis tests and confidence intervals. But for the purposes here, just remember that you divide by sigma over root n when you're standardizing x bar. Okay, so let's do that. So let's just go on to a new slide to get some more space. So I want to compute in my x bar domain the probability that x bar is between 21 and 23. So I now need to standardize this thing. So now I have actually three elements to standardize, namely this part, so the left-hand part, the center part, and the right-hand part. But the standardization will just proceed in the usual way. So this will be the following: the probability of what? Well, 21 minus a mu, so minus 22, divided by the standard error, so divided by sigma over root n, or the square root of sigma squared over n. I'm just going to write it like this for our purposes. So this thing here, okay, so this is the square root of the variance of x bar. So I've standardized this left-hand term here. Okay, we now have x bar minus mu divided by the square root of sigma squared over n. It's less than or equal to 23 minus the mean, so minus 22, divided by the variance, square root of the variance of x bar, so root 36 over 225. Okay, so this is my standardization. Right, let's tidy this up a little bit. If you stretch for your pocket calculator and plug in your numbers, this first term will reduce to minus 2.5, less than or equal to, well, this thing I can just denote by z, where z denotes a standard normal random variable, and by symmetry this thing will give me plus 2.5. So what graphically do I want to work out? Well, let's take a normal distribution here. Assume that this is in the x bar world. Okay, so it's centered on a mean of 22. Let's say here's my 21 and here's my 23. I want to obtain this particular area here. Okay, so I'm between 21 and 23. So it's all of this area here. In my standard normal world, what does this look like? Well, this is centered on a mean of now of 0, because we're now in my z world. Okay, and my corresponding values here are minus 2.5 and plus 2.5. So I want to work out this particular area here, this shaded area. But the key point is that these two red shaded areas give the same probability. It's just that one is in the x bar world, the other is in the standard normal world. And in order to use table 4, we have to work in our standard normal world. Okay, so how can we work this out? Well, I could look up the following. I could look up the phi of 2.5. And if you go to your standard normal tables, that should give you to 4 decimal places 0.9938. Well, what is the phi of 2.5? Well, it's the following. Let's pick some yellow again, if we like yellow. The phi of 2.5 is all the shaded area plus this lower tail down here as well. Okay, because in full, the phi of 2.5 is equal to the probability that z is less than or equal to 2.5. So it's all values of z up to and including 2.5. Okay, this is why over here it's the sum of this yellow area plus this red area here. However, that's not the probability we are after. We are only after the red shaded area. So from this phi of 2.5, I have to subtract the yellow area here. But what is that yellow area? Well, we can easily work that out. The yellow area, so this thing, is the phi of minus 2.5, i.e. the probability of being less than or equal to minus 2.5. How do we obtain that? Well, we are now going to use our previous result. Remember, the phi of minus k is equal to 1 minus the phi of plus k. Therefore, the phi of minus 2.5 will just be equal to 1 minus the phi of plus 2.5. We've already obtained the phi of plus 2.5 up here. This was our 0.9938. Therefore, we can compute the following. So going down here, let's say over here, so the probability that Z is between minus 2.5 and plus 2.5 will just be the following. It's equal to the phi of plus 2.5 minus the phi of minus 2.5, which is equal to 0.9938 minus 1 minus 0.9938, and work all that out. You should get a final answer of 0.9876. Okay, so this is our final solution. So there's nothing inherently new in this particular computation of the probability. Okay, we've just had to be a bit clever drawing on previous results, namely thinking of working out in terms of our phi of 2.5 here, having to subtract our little yellow area down here. Okay, but work through this problem again, see how all the steps come together and how we end up with our final probability down here, 0.9876. Okay, so do be careful in any sort of exam question. Typically in the first one or two parts you might be asked to work out a particular probability based on our original x variable here. Typically in the final part of the question you might be asked to work out a probability based on a random sample drawn from this population. So the key point to remember is in our standardization, this thing down here, in our standardization, when we standardize x bar we subtract mu and then divide by the standard error, namely sigma over root n. Okay, and this was then done in our particular example here. Okay, this was the standardization parts here. But otherwise you then just go to your tables and pick out the particular probabilities that you require. Again, is our answer feasible? Is it consistent in terms of magnitude with what we would expect? Well, yes, we can see that our red shaded area over here and equivalently here is very, very large. It's going to be a large proportion of the total probability, and indeed this is what we ended up with. Okay, so do make sure you are able to distinguish between having to compute a probability for x and x bar, okay, because there's slight differences between the two.